Hi everyone. Today let's talk about section 14.7, Stoke's theorem. So we call that in R2 we have the Green's theorem, right? The assumption given C is a simple closed smooth curve in the xy plane oriented counterclockwise. And R is a connected and simply connected region in the xy plane that is enclosed by the curve C. And F is the vector field. Both the component functions have continuous first partial derivatives in R. We have two forms, circulation form and the flux form. So circulation, let me draw a picture here. So this is curve C, this is the orientation. So circulation, we want to measure how much vector field is going in the direction of C. So along with C, right? So going in that direction. Well, that's the same as find like a, this is like rotation, right? That is the same as double integral of the curl of F on the region R. So when we measure the rotations near the points, the regions, on the regions, right? And how about the flux form? Well, the flux form, so we have the picture again. Right, this is the orientation. Well, the flux, we want to measure how much vector field is going across the curve from left to right. Well, this is the same as measure how much vector field is going outside of this region. Going outside of this region, that's the double integral of the divergence, right? And because divergence measure like how much vector field going outside from a point or a little loop around it, and then curl is measure like the rotation. Okay. All right. Then how do we extend this idea to R3? So in R3, the circulation form of the Green's theorem relates a line integral over a simple closed oriented curve in the plane to a double integral over the enclosed region. In an analogous manner, we'll see the Stoke's theorem relates a line integral over a simple closed oriented curve in R3 inner space to a double integral over a surface bounded by that curve. Okay, the flux form of a Green's theorem relates a line integral over a simple closed oriented curve in the plane to a double integral over the region, the enclosed region. Similarly, the divergence theorem relates an integral over a closed oriented surface in R3. But because when we talk about flux, well, in R3, flux is, we measure the amount of the vector fields flow across a surface. So that we have a surface integral, okay? So we're going to have a surface integral, and we can relate that to a triple integral over the region enclosed by that surface. Okay? So divergence theorem, we will talk about that in 14.8. Today, we will talk about the Stoke's theorem. Okay, so let me draw the picture here. So the Green's theorem, right? So in R2, we have the Green's theorem, and this is the circulation form. Right? We have C and R is the region, right? And we want to measure how much the vector field going along C, so in the direction of C. Okay, so we measure the rotation, that is the curl. Okay, so we have F dot dr of the C equals double integral over the region R, curl of F dA, right? But actually curl of F, well, this is the same as we're looking at the del operator cross product with the vector field and dot with the K vector. Okay, so remember this guy is the 3D curl. Okay, Now, where the k component is just the 2D curve. So far, so good, everybody. So this is a picture in R2. How about in R3? Well, in R3, instead of a curve on a plane, we're gonna have a curve on a surface. We have a curve on in space. Okay, and it also encloses a surface. Let's say this is the surface S. Can you imagine? Maybe I should draw some dashed line. Then you know this is behind the surface. Can you imagine? This is the curve C, so we also have the orientation. Okay, then similarly, the circulation on this C. So we see this C encloses a surface. So instead of a double integral over a region R, we look at the surface integral of S. Okay, and then what is the curve again? Well, the curve is gonna be the 3D curve, and then we dot product with n. N is the normal vector of the surface S. Okay, ds. So this is the picture. Okay, so Stoke's theorem is a higher dimensional version of the Green's theorem. So instead of having a two-dimensional region D, we have a surface S with boundary curve C. So let S be a smooth oriented surface in R3 with a smooth closed boundary curve C whose orientation is consistent with that of S. Okay? So we follow the right-hand rule. So if n is going up on the right-hand rule, then the curve go like this, counterclockwise. So far, so good. Assume f, the component functions f, g, h, right? They have continuous first partial derivatives. And suppose the surface S is given parametrically by R of uv, where D is a region in the uv plane. Assume that the tangent vector tu and tv are the partial derivatives with respect to u and v. Okay, so assume those tangent vectors are continuous on the region D, and the normal vector and the normal vector and it should be divided by the magnitude of that. So let me fix that. Oops, what happened? Okay, let me see. I want to have this guy, and I want to insert this guy, and have the magnitude of it. Magnitude, where is it? Here. Okay, here. Oops. Let me move it back inside. Okay, so this is the normal vector, right? Then we have we have the similar theorem, the circulation. So this is circulation along the curve C equals the surface integral of the curve. This is a 3D curve, so it's the del operator cross product with the vector field F. That product with this normal vector n. Okay, but n is the cross product tu cross tv over the magnitude, but ds is so ds equals the magnitude of tu, tv, and then dA, right? Then the magnitude cancel, so that we just have this formula. So this is how we calculate. Okay? All right. So if S given parametrically by z equals g of x, y in the region D, then we get the fourth integral of f, that becomes, okay, I think it's better to say the surface integral. All right. Okay. So the surface integral of f over s is gonna be, so last time we remember we can use the natural parameterization. R xy is xyz of xy, right? Then our tx cross ty is this guy. So far so good, everybody? Okay. So roughly speaking, that the following two quantities are the same. First, the circulation of the field along the curve C, the outer boundary. Second, the net total rotation of the vector field on the surface S. Okay. All right. So note, Stoke's theorem established the 3D curve test for conservative vector field in the three-dimensional space. If the curl is 0, here I mean the 0 vector, right? Throughout an open, simply connected region D of R, then because it's 0 vector, then this surface integral will be 0. Okay, so it means the circulation is 0 on all closed simple curve, smooth curves D, C, and D. Then F is the conservative vector fields. Okay, remark. If a field has a non-zero curve, then it's not a conservative vector field. But if a field has 0 curve, but its domain has holes, which means it's not simply connected, then the 3D curve test is inconclusive. Remember, the 3D curve test, it requires first the curve must be a 0 vector. Second, the region, right? The region, the domain must be connected and simply connected. So far, so good, everybody. This is the, let me put it here. Domain. All right. So now let's do some examples. Let f of x, y, z be minus y squared x, z squared. Let C be the curve of intersection of the plane x plus z equals 2 and the cylinder x squared plus y squared equals 1. Assume C is oriented counterclockwise when viewed from above. A. Find the work done by F along C without Stoke's theorem by setting up a path integral. Part B. Now find the work done by F along C using Stoke's theorems by setting up a surface integral instead. Okay, so let's draw the picture. So we have the plane and the cylinder x squared plus y squared equals 1. What is that? So x squared plus y squared equals to 1. This is the unit circle, right? And we have a cylinder. And y plus z equals 2. This is on the yz. So this is like a line on the yz plane. So x, y, z. Okay, is this a line? When z is 0, we get y equals 2. When y is 2, we get z is. When y is 0, we get z is 2. Okay, so this is a plane like that. And then it passed through it intersects the surface at this point, and let's say at this point. Okay. All right. Let me draw some picture here. So, oops. So this is the intersection. Can you imagine? All right. And what is the surface bounded by these curves? So this is curve C. The surface is this region inside. Okay, and actually it's flat. So let me just use lines because it's flat. It's the plane. Okay. All right. So find the work done by F along C. So in order to calculate the line integral, we need to find a parameterization, right? And this is a one parameter parameterization. Okay, so one parameter parameterization. So here, because let's see here, because you see when the point on this curve, we have if we project down, so it's like we are on the circle, the unit circle, right? So we can have x be the unit circle, is like cosine t, y is sine t, and then because this point is also on the plane y plus z equals 2, so z equals 2 minus y, which is 2 minus sine t, right? So the parameterization is cosine t sine t 2 minus sine t. Wow. And then what's the t? Because t represents the angle, right? So it's between 0 to 2 pi. And then how do we compute? We calculate the velocity. The derivative of cosine is minus sine. The derivative of sine is cosine. And then this is 2 minus cosine t. So far, so good? Oh, sorry, the root of 2 is gone. Yes, we have to be careful. Okay, let's continue. So the line integral on C is then, well, t goes from 0 to 2 pi. Okay, our vector field minus y squared. Y is sine t, so sine t squared. X is cosine t. Z squared, so 2 minus sine t squared. So far, so good, everybody. Oh, wait a little bit. I want to make the problem easier. So, let's see. Let's get rid of the square to make it easier. Otherwise, the trig integral is gonna be more complicated. Okay. Alright, so this guy, dot product with okay, wait. We use the vector field dot the velocity minus sine t cosine t minus cosine t. And do I have more space here? Oops. dt. Okay, so what is the dot product? Minus sine t times minus sine t is sine t squared. Cosine t times cosine t is cosine t squared. 2 times minus cosine t, so minus 2 cosine t. And then we have plus sine t cosine t dt. So far, so good, everybody? Alright, and now you can see sine squared plus cosine squared is 1. So integral of 1 is t. Integral of cosine is positive sine, right? So we have minus 2 sine t. Oh, okay. And let's separate them. How do we calculate the integral of sine t cosine t? We have 3 ways to do it. One way is because sine cosine, this is 1/2 of sine 2t, then we can integrate 1/2 of sine 2t. Second way, we can use u substitution. Let u be sine t. And then, or you can use u substitution, but let u be cosine t. So there are 3 ways to solve this integral. The easiest, I think, this one, because I can integrate directly. So integral of 1/2 integral sine t is minus cosine 2t, then over 2 in front. Evaluate from 0 to 2 pi. So this means we plug in 2 pi first, and when we plug in 0, it's gone. Then sine 2 pi is 0. Sine 0 is 0. Okay? And cosine 4 pi is 1, but cosine 0 is also 1. They cancel out. So the answer is just 2 pi. So far, so good, everybody? Okay, so that's part A. We just compute the line integrals, right? Part B. Now find the work done using the Stoke's theorems. So the surface integral. Okay, you see the surface enclosed by the curve C, right? Which is this guy, yeah. And now we need to find a parameterization for it. Let me move this guy here. Okay. So B. Okay, how do we get a parameterization for it? Well, here, because now any points on this surface, well, we can use polar coordinate, right? We can let u be theta, let v be r, then x is r cosine theta become v cosine u, y is r sine theta, r is v sine u, and z, because it's on the plane, z is 2 minus y is 2 minus v sine u. So our parameterization uv is v cosine u, v sine u, 2 minus v sine u. And how about what's the u and v? So u is the angle between 0 and 2 pi. V is the radius between 0 and 1. Because it's inside. If you project down, it's inside the unit circle. Right? Okay. Now, what's tu? Derivative of cosine is minus sine u. Derivative of sine u is cosine u. And that guy, derivative of sine u is cosine u. So minus v cosine u. So far, so good, everybody. And then tv is, derivative of v is 1. So cosine u, sine u, and minus sine u. Okay, now how about the cross product? So ijk minus v sine u, v cosine u minus v cosine u, cosine u, sine u, minus sine u. Okay, that equals, let's see. Let's look at the first components. Determinant of this guy. Minus v sine u cosine u minus negative become plus v cosine u sine u. Ooh, wait a minute. Are they the same? Oh, they're the same. So it's 0. Yay. Okay. Next. We get minus j components of this guy, right? Minus become plus. So that is plus v sine u squared. Minus become plus v cosine u squared. Oh, you know sine squared plus cosine squared is 1. This is minus v. And then k components. determinant of this guy, minus v sine u squared minus v cosine u squared. Oh, this is also minus v. Okay, so we have 0 minus v minus v. So far so good, everybody? Okay. So here, our orientation. So our orientation, of C is like counterclockwise. So in this case, the normal vector should be pointing up. Okay. So, but however, this guy, the normal vector is pointing down. So, it's not quite consistent with our orientation, right? So how can we fix it? One way to do it is to switch u and v. Yes, because if we switch u and v, then this guy becomes tv cross tu, and you know tv cross tu is the negative of tu cross tv. So far so good, everybody? Okay, and let's see. Okay, so let's keep this for now, and let's continue to evaluate and see what happened. But keep this in mind. We know the vector we get is like pointing down. Okay, is the vector we get here is pointing down, which is the opposite of what we should have. Okay. All right. So what is the curl of f? Wow, that is the gradient. Sorry, not gradient. It's the del cross f. Okay. If you can remember it, that is hy minus gz fz minus hx gx minus fy. Okay, now let's go to look at our f. What is our f? Negative y x z. So this is f g h. hy 0, gz 0, f z 0, hx 0, gx 1, fy minus 1. Oh, so this is just 0, 0, 2. So far so good, it's very simple. Then our surface integral of 0, 0, 2, dot product with 0 minus v d du, because here u and v, they're just constants, so the order doesn't matter. If we do du first, u is from 0 to 2 pi and v is from 0 to 1. Okay, so when we multiply it out, we just get negative 2v, right? And that is because so that we get so integral, because it has no u in it, when integral of constant with respect to u is just u from 0 to 2 pi. So we just get 2 pi times negative 2, and integral v is v squared over 2, evaluated from 0 to 1. Ooh, so this is 2 pi minus 2. when we plug in 1, you see the 1/2 is there. When we plug in 1 is 1, when we plug in 0 is 0. This guy, we get minus 2 pi. So if the orientation is opposite, the answer is gonna be missing the it's gonna be off by a negative sign. Okay, so let me write it down. Okay, so that is because the normal vector doesn't match the orientation of C. Okay, how so that's why it's off by a negative, because then our normal vector, okay, our normal vector doesn't match with the orientation with of C. Okay, normal vector doesn't match orientation of C. What do I mean? So if your C is going like counterclockwise, this is your surface, then your normal vector should point up. But however, the permutation we choose in this case, our normal vector points down. So that's why it's how to fix that. So how to fix that? Just switch U and V. Okay? Yeah, just switch U and V, and then the TV is gonna be TU is gonna be DV. So when we switch them, you realize the normal vector is like the opposite with what we had before. Okay, so if you switch U and V, then you will get a new normal vector that match the orientation of C. Okay, so we'll get a new normal vector match with the orientation of C. So far, so good? Okay. Yes. What do I mean by switch? I mean let V be theta. Let U be R. Okay? And then you can continue and calculate it, and then you realize the answer you get is 2 pi. So I will leave it as an exercise for you after class, so you can switch the U and V, and then we do this problem and check whether you have 2 pi. Okay? So I actually did before, and I know the answer is 2 pi in that permutation. Okay, but I really want to show you what happens if you choose a permutation that doesn't match the orientation. Okay, you will see the answer will be off by a negative. Okay, so this is a good example. And how to fix it is very easy. Just switch the U and V. Okay, let's continue. This example, let f be the vector minus y squared x c squared, and let c be the boundary curve of the portion of the plane that lies above the square in the xy plane. Assume c is oriented counterclockwise when viewed from above. Find the work done by f along c. Okay, let's see here. The plane x plus 3y plus 10. Okay, so x is from 0 to 1. So 0 to 1. And here also 0 to 1. Okay, so let's see. At the point when x is 1 and y is 0, we get z equals 10. So let's say this is 10. And when, oh, sorry, not 10, 11. Oh, okay. So when x and y both 0, we get 10. And when x equals to 1, we get 11. Okay. And when x is 0 and y equals 1, we get 13. Right? So 13 right here. Okay? So because it's above the square, this is the square. So at 1, 1, when x is 1, y is 1, then how about the z? Is 14, right? 14 right here. So imagine 14 is right here. So it's gonna be a plane look like that. Can you imagine? So far so good, everybody. Okay. But this guy is actually from here. This guy is from here. This is from here. Okay. All right. So assume the curve is oriented counterclockwise. So like this and this orientation. Find the work done of F along C. Well, first we want to find a parameterization for the surface, right? And here, because z is just a function of x and y, right? So we can just use the natural parameterization, x, y, and z is x plus 3y plus 10. Well, then tx 1, 0, 1. Ty is 0, 1, 3. Well, tx plus ty is, oops, what is that? That is the determinant ijk 1, 0, 1, 0, 1, 3. I determinant of this 0, so minus 1, and j, negative j, so and then we have 1 times 3, 3, and then k component determinant of this guy, just 1. So far so good, everybody. Okay, and then let's continue. And then we also need to compute the curl of f, okay? So what is the 3D curl of f? Well, if you can remember, that is hy minus gz, fz minus hx, gx minus fy. H, so this is f, G, and H, right? H, Y, 0. G, Z, 0. F, Z, 0. H, X, 0. G, X, 1. F, Y, oh, Fy is minus 2y. So far so good. So this is just 1 plus 2y. Alright, and then let's continue. Okay, so we compute the surface integral. We have this curl. So 0, 0, 1 plus 2y, dot product with -1, -3, 1. Okay, and we have, well, okay, let's see. X and Y are between 0 and 1. So, because it's a square, the order doesn't matter. We can do dy dx. So what is the dot product? So 0, 0, oh, it's just 1 plus 2y. Yeah, so 1 plus 2y. And when we integrate with respect to y, we get y plus y squared. And when we integrate, so it becomes 1 plus 1 minus 0. So that is 2, right? So 2, and then we integrate up constant with respect to x is just x. Evaluate from 0 to 1, so it's 2 probably 1 minus 0. So the final answer is just 2. So far, so good, everybody? Yes. So, and that's it. 2 is, yes, by the Stoke's theorem, the work done. Okay, so maybe we can say by Stoke's theorem. Okay, the work done, which is the integral on this region C. Okay, so C is this intersection, right? CF dot dr is this double integral, okay, over the region S, and this is the del of F dot product with N ds. And our answer is 2. So far, so good, everybody? Okay, so today we have learned the Stoke's theorem. It's like we extend the idea of the Green's theorem, the circulation form. Okay, so have a nice day. Bye.